Hello, and welcome to our presentation on deep learning and computer vision algorithms for self-driving cars. My name is Brendan Franz, and I'm joined by
Milan Yostis.
Tropicar.
And Travis Boyash.
This is the outline of our presentation today, so we'll be starting off with the motivations for developing self-driving cars. Overall, humans are a lot better drivers than computers, but they're not as reliable. As you can see, there's many factors that come into play for a driver. These factors can range from external conditions to the mental state of a driver. Often, a driver's eyes are on the road, but their mind is not. In a similar sense, their eyes may be distracted and looking at their phone or something else in the car. So while humans can be initially better drivers than computers, computers have the ability to become a more perfect driver. So, there are incentives for developing self-driving cars. First is increased safety. Every year, 1.3 million people are involved in a car accident according to the World Health Organization. Additionally, car crashes are the leading cause of death for children and adults ages 5 to 29. Additionally, 17% of Americans have a 45-minute or more commute every single day to work. So if they're able to use that 45 minutes for doing their work or working on something else they enjoy, we can contribute to increased productivity and increased efficiency. Additionally, integrating self-driving cars with smart cities also allows for a more efficient allocation of our resources. So for our background on the work that's already been done with self-driving cars, before there were any deep learning models, we had computer vision algorithms. Computer vision kind of serves as a set of eyes. Within computer vision, we have image thresholding, where you take the lines from an image, extract them, and place them on a background. There's also other methods to computer vision, like binary processing and histogram matching in images. But on the other hand, with convolutional neural networks, we're able to give those networks a set of data and they're able to extract the patterns. Convolutional neural networks work with spatial information processing. So in our case, they would process the images, detect the road lines, and determine the angle that we should be turning at. So for our project specifically, we had a few objectives and goals. The biggest one was to improve performance in adverse conditions, specifically with shadows. If you look at the image in the top left corner, you can see that as the car is driving, it creates a shadow on the line that we are trying to detect. So with computer vision, when you go through and do your thresholding, there is a gap in the line because of the shadow that's created. This obviously creates an issue on a more large scale when there are many cars doing this, or as you see in the bottom image, there's another obstacle like a tree casting a huge shadow over the line you were trying to detect. While this was one of the bigger issues we ran into, other adverse conditions include sharp curves, unclear white lines, overexposing sunlight in the camera, rain, poor pavement conditions, and puddles on the road. So for our experiment, we have the following design. Our test course, our outer lane is 86 meters, our inner lane is 71 meters, and then on our track we had red dots that served as stop signs, so we could accurately record when a whole lap stopped and began. We have the following test car. It is Lawrence Tech's Actor 1 vehicle. It is a Polaris GEM electric car. It operates with a drive-by-wire system, uses a Mako camera to pick up images, and it is running using a Ubuntu Linux computer that is running the ROS and Python programs. And then for evaluating our demonstration, we had the following chart. We were trying to complete Linux computer that is running the ROS and Python. Sorry, I didn't hear the question. Oh, I'm good. Okay. So we have 5 laps for the inner, 5 laps for the outer, and we were tracking what kind of weather conditions we were doing the test in.
We have two methods, as said before, for our vehicle. The first one is the traditional algorithm, which uses the vision-based system rather than AI or deep learning. The traditional algorithm is created as a sort of contrast to the deep learning one that we will be talking about soon. It will be able to identify the areas that vision-based deep learning or vision-based self-driving struggles in, and what can be improved upon by either deep learning models or for possibly hybrid models in the future. Now, for the traditional model, it is imperative mainly to get the pre-processing correctly finished so that the lines can be properly detected so that it can actually follow those lines for the lanes. So the first obstacle that comes up is the difference between white and yellow lines. So the pre-processing for the images for the vision-based program identifies and removes the yellow lines. It finds the shaded areas, as you can see here, and gives them, it colors it in two different colors. So you can identify which areas are shadows and which ones are not. It then dilates and erodes against those shadows to give you a more uniform area of where the shadow actually is. So you can see right here is the white line that we're looking for. When you take the shadow, not the white lines don't necessarily always get included in that shadow as they are of higher contrast than the rest of the shadow. Dilating and eroding it gives it that line back and allows you to then pre-process it and increase the brightness in order to sort of level out the image more and make it more uniform. So as said before, you can apply a brightness mask, bringing the brightness of the shadow up back to the approximate level of the rest of the road. You can then adjust the contrast, which gives you a significantly more well-defined white line for the program to be able to identify, and then you can find the contours in the shadows with less difficulty and more reliability than with just identifying the contours previously. In order for the lane following to work, it identifies the white lines for the lane. It will then dilate those in order to fill in any gaps in these poor road conditions. So if the white line has gaps because the pavement is cracking, the dilation can expand the contours that it finds and start connecting them together into one more uniform line. It will then take the 5 largest contours and extend them. So you can see right here you have the dashed line, and right here you have 2 sort of lines that connect together. And that's because it extends those contours together, making it into one more well-defined line that it can follow in a more smooth sort of pattern rather than sort of jittering around the corner. This helps it identify the dashed line, and it also, gives it the more sort of clean turn that you're looking for when going around the corner. The lane following is based off of primarily identifying the 2 most probable lines for the lane that you are currently following. It begins off with you starting in the center of the lane and identifies the 2 lines that are closest to where it would expect the lines to be. It then, when you begin moving, it bases its new predictions on the most probable lines off of the previous lines that you had defined. So when you move forwards and it takes a new image, it knows the coordinates of the 2 most probable points, and it checks for the contours closest to those 2 points before deciding which ones are the contours it should follow. It then determines the center point of these 2 and draws a little blue dot there, and it uses that to identify whether it should turn left or right based off of how far it is off of the center line of the view. There are a few problems that are there are a few problems with the traditional algorithm that can be solved in the future, or possibly with a mix between deep learning and traditional algorithms. The main problem is that when turning around a sharp corner, it can sometimes lose focus of the inner lane. So you can see that the white lines for the inner side are being cut off and cannot be seen. And if the vision-based system is unable to see the lines, it It can't identify them, and it can't predict that it needs to make the turn. Other than that, the sudden extreme changes in lighting conditions means that the pre-processing does is it slowly adjusts to the level of lighting that is currently, it adjusts the lighting level to better fit what it's supposed to identify. However, this takes a little bit of time. So if the sun comes out from behind a cloud all of a sudden and the brightness of the image goes up significantly, the program can sometimes have a little bit of catch up to do, and during that time can steer off the course. There are a few solutions that can be applied in the future for the issue of losing the line when turning around sharp corners. A wider lens can be used, or if we had more time, you could create a prediction of where this vehicle should be turning based off of the previous images that it's taken. Otherwise, increasing the processing speed would allow it to more quickly adjust to the changing lighting conditions, or it is also very possible to stop the vehicle when the lighting changes too quickly.
Well, Milan described what would be a vision-based algorithm, or the eyes of a model, and it still has considerable flaws. Our team asked ourselves what exactly is a stronger organ than the eyes, and of course we landed on the brain, thus leading to our development of Project Deep Steer, a deep learning model to be able to overcome the limitations of traditional computer vision algorithms and to be able to more accurately adapt to different weather and lighting conditions. When it is sunny, rainy, or cloudy, or when there are those sudden fluctuations in light, we created this deep learning model to be able to more accurately be able to adapt to these varying conditions. To be able to do this, we developed a convolutional neural network, which is a sequential model, meaning that we developed it from input to output. And convolutional neural networks, specifically ours, have 4 different types of layers. Convolutional layers, which extract different types of features from the images that are inputted into the model. Dense layers, which classify the different features that are extracted from the convolutional layers or from the outputs of the convolutional layers. Max pooling layers, which distinguish the most distinct features from these extracted ones. And flattened layers, which take the 2-dimensional output of images and essentially flatten it into a singular dimensional layer of images. While we selected a convolutional neural network as our model, there are several other types of neural networks that are being commonly used for self-driving. One of these is a recurrent neural network. However, the reason that we did not select a recurrent neural network is because recurrent neural networks work better with time series data. So if we measured the time at which the cars finish laps around the laps, or if we measured solely the velocity of these vehicles, then a recurrent neural network would be more optimal. However, since we were analyzing input images and linked velocity messages, we decided that a convolutional neural network would be better for this. A specific type of recurrent neural network that is especially used for self-driving is a long short-term memory network. And these primarily are used for trajectory prediction or object detection, as it can take the history of movements and be able to predict future movements based on this. However, again, since we were using input images and convolutional neural networks use image processing as its main tool for analyzing, we decided a convolutional neural network would be better. There has even been work done combining these 2 models to develop a recurrent convolutional neural network. While these are the most advanced model and they yield the best results, this, however, would have been too complex of a model for us to program with the time constraints that we were given. For our convolutional neural network, the APIs that we use are TensorFlow and TensorFlow.keras to be able to define the model. With TensorFlow.keras, we use model.compile to actually configure this model to ready it for the training and evaluation process, and model.fit to be able to actually split this model into one batch of 10 epochs each and repeatedly iterate over this data sequence in order to be able to train based on that model. We also use scikit-learn to randomly split the hundreds of images that we give the model for processing into testing and training data with an 80-20 split of training to testing data. And now Travis will talk about how we collected data for our model.
So we spent a lot of time trying to get data from a bunch of different weather and lighting conditions. As you can see here, we have some rain data. And after we got this data by subscribing to the drive-by-wire system and the camera, and essentially trying to drive and model good turns and lane centering for the algorithm to follow. Then we used the APIs that Shelby mentioned previously to actually make the data set and feed this data into our models. So in contrast to the computer vision algorithm, we kind of went with the simpler route in terms of pre-processing. We just cropped the image and resized it to cut out all this noise and trees and things like that in the background, and only focus on the lines. And this was done to preserve the shadows in different lighting conditions in order to improve the robustness of our deep learning algorithm. So it has a lot of different conditions that it's used to. Okay. And then we used a extraction program which took the path to the image on the computer that was taken with the ROS bags and attached the yaw rate at that most recent time to the image in order to make the data set. And these labels were used to then train our model later with TensorFlow. So yeah, here's our statistical results from after training. We eventually got our loss down to 0.001 and our mean absolute error down to 0.02. And then after getting this, we used these predictions to actually maneuver the car with the drive-by-wire system. So here's the testing data, which is unforeseen data that the model has never seen. And as you can see, the loss was around 0.03 and it got down to almost 0.009. And yeah, this data was used to maneuver the car, and the turns were as close as we could possibly get them after feeding many, many ROS bags into the model. So now I'm going to talk about results and future work for our project. So as you can see, we did a demo yesterday, and our deep learning performed pretty well. It got 5 laps on the inner and outer, and our computer vision got almost 3 and then a little over 4 laps on the inner and outer. The computer vision did take a little bit less time and was a little quicker, and as you can see, our deep learning took a little bit more time on the laps there. So if we had more time in this program, I think that we definitely could have used a hybrid approach, which has shown good success in the literature and with the other team, and may have done better for our program in the future. And we would have also liked to get more data in a more expanded variety of weather and lighting conditions and feed that into our model. And I think that would definitely would have helped with our results in the future. So yeah, that's it. Does anybody have any questions as of now about the model or any of our algorithms that we worked on?